I gave a talk about this at the April meeting last year in Santa Fe. So this is a little bit of an update now that we've been going a little bit. And it's nice that Doug Cothe went ahead of me so he could tell you about the Exascale program. So this is one of those applications that Doug talked about that's in that portfolio of exascale computing applications. So this is a partnership between Oak Ridge, Lawrence Livermore, Los Alamos, and NIST. And so I've listed the team up there. My co-PI is Jim Bielak at Lawrence Livermore, and then Kurt Bronkhorst is the lead from Los Alamos, and Lyle Levine from NIST. And again, so it's about how we can use exascale computing to push forward some of the understanding and applicability of additive manufacturing. A little bit about terminology. One of the common terms for additive that you also hear is 3D printing. It's often used, it's a term that MIT started using a lot, mainly for the polymer kind of things. A few years ago, you started to see a lot of machines on the market in the several $100 range to make plastic, polymer parts. Another term that goes back to the early days of this technology is rapid prototyping, and that was one of the main applications in the early days, was coming up with designs and trying them out in a rapid form. But that was, so not meant to produce final parts, but to prototype design parts. But now we're at a stage where we're actually making final and near final parts. It's a big field. It's rapidly moving. What I'm going to be talking about is what's very exciting is now we're doing this with metal, with titanium, nickel-based alloys, stainless steel, a variety of things. So the term additive is the one that's used a lot, and it's to differentiate between technologies where you're usually starting with a chunk and you're removing material. Instead, in additive, we're building up a part piece by piece. A quick slide on the advantages of additive. Complexity is almost free. It's a little bit of an exaggeration to say it's completely free, but you can get very complex designs, and they come out of the machines nearly ready to use. There is some post-processing that often needs to be done, but you can get some very complex parts right out of the machine. There's typically less waste in the process, and you can go and repair parts. So that's another attractive thing. You can some of the technologies you can actually repair defects and breakages in existing parts using some of the same technologies. You can replicate parts. You can scan them in and get a copy of a part that you already have that exists. So those are some of just a quick summary of some of the advantages, what makes this attractive. You'll notice that I didn't say here cheaper or faster, and that's sometimes not really where additive pays off. The big payoff really is in the top left up there, the complexity, and this ability to really think about designs in a new way and come up with new parts. So how does it work? Very quick overview. Start with a CAD model of a part. You mesh it up with a surface mesh. You slice it into 2D slices, and then you build it up layer by layer. So this part that I'm showing is obviously a cup, and it's a ceramic or plastic part. And what I'm talking about is metal. And for metals, those layers are 50 micron type size. So we're starting with powder and building up a part. So many layers to make a full part. It can take hours or days to make a part, a large scale part. There are a number of different technologies ranging from where you blow the powder and hit it with a laser or some power source and melt it as it's being deposited onto something, to where you have a bed of technologies where you have a bed of powder and you're hitting it with a laser or electron beam. But all of them have a lot of physics in common: melting and solidification, thermal transport, solid-solid phase transformation, and repeated thermal cycles, sometimes completely melting and resolidifying and sometimes not. But that complex physics, a lot of it is similar to welding, which obviously has a long history of expertise, but a lot of things are different. More rapid solidification and different aspects that make the science base for welding is helpful, but not really complete. For this project, we're focusing on the two powder bed technologies, laser and electron beam. And you've got some movies down here. This is a laser, and one of the things you can see from that is the spattering of parts of molten drops that are coming off. That's a concern in that technology. The middle picture is a close-up, very high-speed camera of a laser interacting with the metal particle, metal powder particles. On the right, you have e-beam process, and one of the things you can see is the spatter is less. You have a sintering stage that happens that kind of locks the powder in place, and with an e-beam, you can move the beam much more rapidly than you can with the laser. There are pros and cons of each technology, and certain features that are better with one or the other. Surface finish differs and things like that. But they share a lot of characteristics, starting with the powder and hitting it with an energy source and melting it layer by layer. So what happens is you have a table that has this powder on it. A blade comes out, spreads a layer of powder. You hit it with the beam, either electron or laser. Then the table goes down, you spread another layer and do it again, and just do that repeatedly. And the table actually goes down, and you get a new layer each time. So that's how the thing works. That all sounds great, and there's lots of excitement about it. There are lots of challenges, though. The microstructures that you get out of this technology are quite different from what you get out of traditional manufacturing. And I don't know if you can see up on the upper right. On the left, you have kind of a typical microstructure out of a traditional process. And you can see it's fairly uniform grains and nicely distributed throughout the picture there. On the right, you have a mess. And that's what you get typically out of additive. And the grain structure is all over the place. It's oriented in different, you've got some alignment along different axes. But it's really not what you want to see. And you have, unattractive material properties out of that kind of part. And you can see the strength of the parts. This is just using typical approaches. With additive, you get quite different strength properties out of the two. The good news, though, is that the microstructure that you get out of there is very. You have a lot of control in additive over the process parameters: the beam diameter, the beam power, the beam velocity. Even the scan path between the scan strategy between just going back and forth, going in some space filling curve approach. So one of my colleagues likes to say it's definitely one of these good news bad news things. You have tons of parameters you can set in additive to control the process. The disadvantage is you've got a ton of parameter space that this huge parameter space, and you don't really know what's optimal. And that's where the need for where simulation can help. And so all of these, the process parameters are directly tied to the microstructures that you get in your final part. So this is another picture of just a simple. Making a simple cylinder and illustrating how you get very different microstructures at different parts, different locations in the part. Down at the bottom, you get one type of microstructure. Up at the top, and this is because the geometry of the part, the thermal cycling between layers and different locations, the base is heating up as you go up in the part. So all of these things you need to be able to analyze, and right now the machines are making parts, right? And the control systems that are coming up with the scan strategies and the beam parameters and all of that, they're fairly heuristic. I mean, they work, but it results in a lot of trial and error to come up with the best parameters for a particular part. And you can control all these things, but it takes a lot of trial and error. So I mentioned this linkage with the process parameters. So just to make that a little more explicit, these process parameters, everything from the feedstock properties, the powder itself, the distribution in sizes, and the purity, and all of that comes into it. The scan pattern, the beam power and velocity, and just how it goes across the surface. All of that leads to the microstructure itself, the grain structure, the orientation, the grain boundaries, porosity, all of that stuff, which directly affects the properties of the material and then how it performs in a particular application. So keep in mind that the desired properties are dependent on your application. So you may need different materials, different processing parameters, and there's always trade-offs economically between how fast can I turn out a part. That's going to, if I have more time to spend, maybe I can do preheat the box and or do a post heat treatment afterwards and alter the grain structure that way. So all of these things come into play. But it's really this whole linkage from the process all the way to performance that we call the process structure property performance relationship, and it's really a big a bit of an unknown for AM to have a complete understanding of that. So how does simulation fold into this? At each of those stages, the process structure, properties, and performance, we have various codes that have been put together over the years both in industry, commercial tools, and at the labs to do different parts of this. Fluid flow, surface tension, heat transfer, all of those things are directly, modeled. We can simulate those things from the process side. We've got a variety of codes and methods, phase field, cellular automata, to do grain growth and the microstructure formation. And then polycrystal plasticity, various approaches to get them to transfer from a particular microstructure to the properties that material will have. And then thermomechanics codes, solid mechanics to get the internal stresses and failure modes of the final part. And there's a lot of activity going on across this, in different pieces of this. What's not done as much, and what we're trying to do in this project, is tie all of this together in a coherent fashion. A lot of times, everybody's seen this chart or a variety of variations of this chart for multi-scale material modeling over the years, going from quantum atomistic all the way up to parts and systems. And I just want to make it clear that we're, in this project, focused solely on that middle range from mesoscale up to part scale. We're not going down into atomistic or quantum, and we're not going up into systems. So we're squarely focused on that part scale and down to mesoscale of what's happening. Similarly, the whole field of additive manufacturing has a big range of topics where simulation can play a role. From the things I've talked about, like fluid flow and heat transfer in the parts, to data analytics. These boxes, when they make parts, have an extensive amount of data that comes out. So you can look at that and correlate successful builds and failed builds to environmental things and things that the machine was doing. We're not really going into that. The whole process modeling piece needs to be wrapped inside of an optimization loop to look at shape and geometry and topology to improve designs of parts, because, as I said, one of the main advantages of additive is this design flexibility. So again, we're not really looking at that part of the problem, the topology and shape optimization, but what we're doing should fit into that. So again, to be clear, what we're focusing on in this particular project are those process, that linkage between process, structure, properties, and performance. So that means the microstructure, continuum scale models for the fluid flow of the melt pool, the thermomechanical modeling of the parts, and also tying to experiments to validate. So this is a picture I'm going to use a number of times throughout the rest of the talk, where we kind of tie everything together in a little different way. It's because it's not really that linkage between process, structure, properties, performance is not really linear. It's more of a linked workflow or relationship, where you have the things happening at the melt pool, which is really controlled by that process, those process things, driving the microstructure and the properties, and then linked back up to the part scale thermomechanics, where you have, and we're not really looking at all aspects of performance. What we're using as a surrogate for that is really the residual stress that you see in a part at the time of a build. So really that linkage between, so those things in the green boxes are really where we're focusing, and it really needs to ultimately be tied to other things like the powder behavior and topology optimization at the larger scale. So in this, this is the same picture again, but now I've added some of the code names, and I did not include I've got a couple of slides that go into a fair amount of detail on these codes, but I kept that out of this particular talk. I'll just say a few brief things about a few of these. So some of these are actually new efforts in this project. ExaConst. I'll say a little bit more about that later. Polycrystal plasticity, solid mechanics code, ExaCA, a cellular automata code. But we're leveraging a lot of things that have existed and been developed over the years in the labs, like Truchas, which was originally a casting code created at Los Alamos. AL3D, Diablo is a solid mechanics code at Lawrence Livermore. But the point is that there's no code that exists that can do all of the physics we need in one environment. So we're linking these things together to build more of an environment that can go after this problem. From the exascale standpoint, most of the cycle requirements, the computationally intensive parts of this problem are at the microstructure and the property level. So what that means is we're not really talking about a single code or a single application or component that needs to scale to the entire machine. It's really more about some continuum level simulations that are firing off dynamic asynchronous subgrid models of hundreds or thousands of those to inform the larger length scale models. So there's been a lot of work on this over the years. This is a reference, a really nice paper here that goes through a number of different approaches for multi-scale approaches, like what we're going after. But it's important when you look at this to think about how we're going to use the exascale machine. It's a little different than some of the other applications in the portfolio. in that we, maybe a phase field or a cellular automata model or the plasticity code may only run on one node or a part of a node, but there may be hundreds or thousands of them in a coordinated fashion. So we're thinking this might be a role for machine learning. I'm a little bit of a novice in this area, but it's something that we're intrigued by. Can we use machine learning in two potential ways? One is to know where to optimally do the sampling of the lower length scale calculations, and also how to maybe on the fly build surrogate models from those sampled lower length scale simulations, because we can't afford to do it everywhere. Even with Exascale, we're not going to be able to sample everywhere. So Doug mentioned the ExaLearn Co-Design Center, so we're in discussion with that project about how best to kind of pursue this area. So we're driven by test problems. You've probably seen this before. You've heard me talk about it in other contexts as well. Using a series of challenge problems from single melt pools to multiple melt pools, single tracks. So building up a more and more complex set of problems for the components to go after, and then the coupled capabilities as well. One of the reasons I mention it is that this is an important role for NIST. They've initiated a community benchmarking activity. The first workshop was held a couple of months ago in June. Basically, they, in part informed by this project, have come up with some challenge, benchmark problems, perform the experiments, but don't publish the results. Publish the specifications of the problem, do the experiments, measure residual stress, and look at the microstructures and things like that. And then everybody comes to the workshop, presents their results, and see who does best on the simulations. It's a great thing for the community. It was a huge success, I thought. Some really nice talks, and it was great to see the community willing to share, come in blind, share their results, and compare and say, here's where we did well, here's where we didn't, where we need work, and so we think this is going to be a real benefit, publishing these benchmark problems to the community and working to solve them. I'm going to go quickly through a couple of those example problems. This is a little arch that we're using. It may be hard to see here, but what you can see is that on the right-hand side over there, when you cut the part from the base plate after you build it, it springs up, so that gives you a good indication that there was residual stress in the part. So NIST built this part in a number of titanium with a number of different scan patterns and process parameters, and then measured residual stress. We've simulated that part using Diablo by itself. I won't go through the whole movie because I'm running out of time. But then we've done that, compared it to the experimental results. It's pretty good. It could be better though, and that's why the project exists, to make that better. Another experiment that we compare to and use as a driving problem is just a single track. It's not even using powder. This is more like welding. Take a bare metal plate and run a laser along it with different velocities, different powers. And you can take that, slice it, and look at the melt pool, the shape of the melt pool, and get a really nice look at the grain structure. We use this to drive a coupled simulation between the melt pool. I'm going through this quickly because I'm running out of time. So what we can do is take that melt pool, pull out one specific location, and do a phase field or cellular automata calculation, and that's our first kind of coupled result, linking the process parameters also, to the microstructure. And we did that using Truchas and one of the phase field codes. And you can see the picture here. One melt pool along a scan line, pull out one little several micron cube, do phase field, and watch the grains grow. I'll skip through some of this. We've also done this with cellular automata, much more computationally efficient. Still a little bit of a question how these things relate. But this was a nice result because we can see the difference between doing fluid flow and no fluid flow on the shape of the melt pool. We're also coupling the process scale or the melt pool itself, the thermal history, with the part scale. So in other words, take that Truch's code, which does the fluid flow and behavior of the melt pool, with the part scale thermomechanics, the Diablo code. And this is our first example of an in-memory coupling. We did first file-based, but now in-memory coupling. And we've got those results in a recent milestone for the project was to show that. We just did it for a single melt pool, but it shows that the capability works. Another one that is currently in the file-based coupling stage is the coupling between the microstructure and properties. So we've demonstrated that. Next phase is doing that in memory. I'll go just quickly through that. So I mentioned this ExaConst code, which is essentially this part of the problem is often Abacus is a common commercial tool that's used for this type of calculation, but we envision this as a much more scalable GPU performant capability that's going to be of great interest, I think, to the community. I mentioned that we've done this integration. It's not really coupled yet. It's write out a file from both. We've done it with both phase field and cellular automata. Read that in from the property side and do a 1,000-grain polycrystal plasticity calculation. So you can see what we're doing here. We've got this picture of different of all of this stuff eventually has to be linked together, and we're doing these binary linkages first via files and then in memory. We've not yet done the property part scale. That's another step. So just to wrap up, what we envision as success of this project is, we kind of view this almost like a DNS. There's a big community doing simulation for the process part of AM, but they're not doing it at this fidelity with this level of coupling. And so we envision this being kind of a sort of analogous to DNS for CFD. We can look at things that may not be possible with other capabilities, like the real effect of fluid flow, the real significance. It's a big question in the community. We can look at things like inoculants to adjust the surface tension, which there was a nice paper in Nature recently about that possibility. We can look at machine designs, the actual additive manufacturing machines that don't exist today, and investigate what they might be possible. Use it to develop and calibrate reduced order models. We won't be doing the actual developing of those, but we can use them to show you where a reduced order model falls apart, where it's good, where it's not good. And then this will be a community package. At least the infrastructure and the APIs will be published, and most of the components are open source or in the process of being developed open source. Some of them are export controlled and so won't be there, but the entire framework or environment will be. So I should probably just wrap it up there. I don't know if we have time for a question or two.